Let's now consider an integration of a quantity over the following region. Let this point be the x equals 3 point, and let's let the region be a circle of radius 3. Let's just say the upper half of the circle of radius 3. Then that circle is going to have a point here, so let's see if we can sketch a reasonable semblance of a circle. Now we want to describe this region. We want to do an integral of some quantity over this region. It might be a moment of inertia, it might be a mass, it might be the volume of some solid, curved, plane, whatever, above this region. But whatever it is, we're going to have to partition either the x or the y part of the region and set up an integral. So let's partition the x. So we'll partition the x interval, and that'll be the interval 0 less than or equal to x less than or equal to 6. I'm not going to bother writing down a detailed partition, but we consider a typical interval on that partition. Call this the ith interval, and we'll have an x sub I star within that ith interval. Then the part of the region that corresponds to the ith interval is going to be this, the ith x interval, and we're going to have to partition that interval with respect to y. Now that interval will go from 0 to whatever the y value is here, and we'll have a typical j'th partition or j'th interval with sample point yj star somewhere within the interval. And the question is, for the sample point xi star, what is the y interval? Well, the y interval goes from 0 to whatever this is. What is the value going to be here? There are two possible approaches. We can figure this out geometrically by simply understanding that the center of the circle is 3 and its radius is at x equals 3, 0, and its radius is 3, giving us this triangle. Now if we pull that triangle out of the circle so we can label it, it's a right triangle. This side is 3, this being a radius of the circle. This side runs from x equals 3 to x equals xi star. So x equals 3 here, x equals xi star here. So what's this side? Well, it's just xi star minus 3. So the triangle has side 3, side xi star minus 3, so that this side, by the Pythagorean theorem, is going to be the square root of 3 squared minus the quantity xi star minus 3 quantity squared. Now that can be simplified, but right there is an expression that gives us this distance. So now we can answer the question about the y interval. It's 0 less than or equal to y less than or equal to, not going to bother simplifying that for the moment, but that's 3 squared minus x sub I star minus 3 quantity squared. Now we'll go ahead and simplify it. That's going to be xi squared minus 6xi plus 9. We're going to be subtracting it so that the 3 here and the 3 here will subtract off, and this is going to be then the square root of 6xi minus xi squared. The same result could also have been obtained by writing the equation of this curve. This curve having the property that if xy is a point on the curve, then the x minus 3 squared plus the y squared has to equal 3 squared, and this can be simplified. We end up with negative 6x plus x squared plus y squared equals 0. And if we solve for y, again, we get y equals the square root of 6x minus x squared, so that if our x coordinate is xi star, we immediately get this this limit on our x value, on our y values. It's also worth noting, and I'll just note this off to the side, that this is the upper half of the circle. X minus 3 squared plus y squared equals 3 squared, which again has solution y equals plus or minus the square root of 6x minus x squared. I was actually a little careless up here. If we solve this for y, we do get a plus or minus, but we just implicitly chose the plus because the y values are always positive here, and the value of the square root must be positive. If we wanted to do the whole circle, then we'd be bounded above by the circle y equals square root of 6x minus x squared, and below by the half circle y equals minus the square root of 6 minus x squared. Whatever strategy we use to model this region, we see that if we partition x first, then our sample point xi star will correspond to a y interval that goes from 0 to the square root of 6xi minus xi squared. And this leads us to our expression for any integral over this region. Skipping some steps now, not actually writing out the summations, but that's something you should do until you're really comfortable with this. We find that our integral of whatever function we're trying to integrate on this region, let's just call that some function f of x, y, can go from 0 to 6 with respect to x, and that implies that our y has to go from 0 to 6x minus x squared. Now the quantity f of x, y that we're integrating could be a density, so that we get the mass corresponding to this region. It could be the height of a curve above the region, in which case our interpretation would be a volume. We could be calculating a moment or a moment of inertia, in which case our f of x, y function would be something even different. And in any case, we probably want to consider what it is that we're evaluating on our small increments. So we're probably going to want to look at wrong color here. So we're probably going to want to look at a typical xy interval and ask ourselves just what quantity is it that we're trying to integrate, so that we can obtain the correct f of x, y function to go in here. Now, we could have started by partitioning the y interval. So again, we're going to pose the question,